Round 2, ding. One of these days we're going to have a little race. We'll see if I can get Wimba set up before everybody gets here, and then I'm going to give a quiz. We'll see who wins. So I have started grading the exams to the tune of, I've downloaded all of them and unzipped them all and started flipping through them and going to start allocating points appropriately. But anyway, so they're not done yet. Other than that, any questions that you may have? You moving on the lab? Got the table-based scheduling done? Deterministic priority queues? Good stuff. So what you're using, you're not using a FIFO anymore because a FIFO implies an order. You're not using a priority queue, you're using a table to represent your priority queue, but it implements a priority queue. If you're real slick about this and you've done everything right to date, all that you should really have to do is throw out your existing FIFO.c and put in a new FIFO.c which wraps a set of functions that you call into table.c. So you got FIFO create, which calls table create. And table create instantiates your table. And when you call FIFO remove, it calls table remove. And table remove queries the table and sees what's there. So really, you shouldn't have to go through and change your scheduler or your semaphores or anything else in response to the fact that you're now using tables instead of FIFOs. Would have been nice to actually do it right in the first place. I tried to talk to you about modularity. Didn't I tell you about modularity? Didn't I tell you think about this stuff? I mean, this is not... Anyway. It's not that I'm trying to be obfuscated on purpose, Mitch. I promise. Anyway. All right. Onward and upward. So we've got to get back in the zone of talking about technical stuff as opposed to exams and exam overviews and other stuff. So this is new material for the first time in quite a while. Well, I wish I could say new material, since I already gave the first part of this set of slides, so it's going to be old material for a few minutes. Priority inversion. So if you remember about priority inversion, we talked a little bit about this already, and I'm just going to go back and briefly review what I've already talked about, and then we'll dive into what we do about priority inversion. So if you remember, up to date, what we've been talking about is that we have a set of independent tasks, and this holds in Lab 8, that you have independent tasks. Tasks don't have shared critical sections. Because of the fact that tasks don't have shared critical sections, does that mean that a task cannot have a semaphore? Do your tasks have semaphores in Lab 8? But what's a semaphore for? So we're using the semaphore as a mechanism to block itself. It doesn't have a shared critical section with any other process. So all that we're doing is leveraging the semaphore in order to use its block queue to remove that process from the ready queue. Okay, so yes, the process has a semaphore, but no other process competes for any process's semaphore. The only process that competes for a process's local semaphore is that process. So we have a set of independent tasks, no shared critical sections. So what happens if we now relax this assumption and start to talk about how, let's suppose we have shared critical sections or shared resources, and we protect those resources with semaphores. Can resource sharing impact schedulability? Now, I wouldn't raise this question if the answer weren't a resounding, oh yeah. So we've got to figure out how this impacts schedulability, okay? So let's consider just the impact of using resources with a simple example where we've got two tasks, A and B. A is higher priority than B. A gets released, B gets released at the same time, and they are both competing for the CPU. Since this is priority scheduling, A will win since it's higher priority. So A runs for a little bit, and at some point during its execution time, it enters the critical section. The thing that it does before it enters the critical section is it grabs the semaphore. Why does it grab a semaphore? Because it wants to make sure that the critical section is indeed executed atomically, or that it's not going to enter the critical section while some other process is in the critical section. So it grabs the semaphore, and it executes the critical section while owning the semaphore, and then it releases the semaphore, and then it proceeds to compute after that, where it's executing code that is not part of the critical section. And then as soon as it's done, it grabs its own semaphore and blocks. Okay, so this is what we have right here. At this point, that's C sub A. That's the worst case execution time for A. Or in other words, the total compute time for A takes up this much. Part of the compute time is the time that it takes for A to execute in its critical section. Okay? As soon as A goes to sleep, B is allowed to run because it's the next highest priority process. B runs for a bit, and then it grabs the semaphore because it's going to execute in that critical region. And let's suppose that its access of the critical region takes longer because it does more stuff in the critical region than process A did. So it grabs the semaphore queue and executes for 3 chunks of time instead of the 1 chunk of time that A executes owning the semaphore. It relinquishes the semaphore, continues to process outside of the critical section, and then it gets suspended at this point. It gets suspended not because it's done, but because at this point A gets released again. So at T sub A, this is the period for process A. Process B isn't done yet. It still wants the CPU, but because of the fact that A just got released, that means A gets to run because it's higher priority. So A runs for a bit, grabs the semaphore, executes the critical section, releases the semaphore, and runs for a little bit more, goes to sleep. B is able to run again, and then it finishes after running for a while. Okay? So this is the scenario we're looking at. So in here, everything's great. The fact that we have semaphores doesn't really impact anything. So that happens only when the lower priority process gets preempted when it doesn't own the semaphore. What happens if it gets preempted when it does own the semaphore? So let's suppose the scenario is like this, where we have A running here, grabs the semaphore, does the critical section, lets go of the semaphore, and continues to execute. Then we have it's done with its compute time, so it goes to sleep. B runs, and then later on in its execution, B grabs the semaphore, and it starts executing the critical section. But while it is in the middle of the critical section, we get an interrupt. Do we block interrupts in the middle of a critical section? I'm getting a few no's. Do I have any yeses? Do I have any? I don't want to say. Not going to admit it. Not going to say it. We block them momentarily in order to control the access to the semaphore. But we want to execute the critical section with the interrupts enabled. We want to allow a process to get interrupted during a critical section. Why is that? Well, you can have interrupts that have nothing to do with the critical section, right? But the whole benefit of a real-time operating system is its ability to allow applications to be developed which can respond close to immediately to external events. The way you respond to external events is through interrupts, okay? So an interrupt can occur whenever, and you want to be able to have a situation to where when an interrupt occurs, you want to respond to it as quickly as you possibly can. The time which the interrupts are disabled limits your responsiveness to external events. So one of the metrics of quality of a real-time operating system is what's the maximum time that you have interrupts disabled for. Okay, and that gives you a dictate of when is the worst case scenario when you could have an interrupt occur, but you don't understand that it occurred or you don't see that it occurred for how much time. So, a millisecond, 3 seconds, 5 seconds. We want, if we disable the interrupt during a critical section, what if the critical section takes 10 milliseconds to run? And you want to have a responsiveness in units of microseconds. So that's bad if you disable the interrupt during a critical section. So we want to, and that's the whole point of why we're using semaphores, is we want to make sure, number one, that the interrupts stay enabled during the critical section. Okay. So interrupts can be enabled during the critical section, and most specifically, an interrupt occurs right here in B it occurs while B is running and while B owns the semaphore. So at that point, that interrupt occurs. The interrupt invokes the scheduler. The scheduler figures out, oh, A's period is up. It's time to re-release A. So A gets released. And then the scheduler gets invoked, and the scheduler says, oh, A is a higher priority than B, so I'm going to run A. So B gets to sit on the ready queue while A gets to run. A runs without owning the semaphore for a bit, and then it attempts to lock the semaphore. And it just does a strong P right here. As soon as it does a strong P, it says, wait, the semaphore is not available. A gets sent back into the block queue of that semaphore. And then because it's on the block queue, it doesn't want the CPU anymore. The only process left is B. So now B gets to run. So B runs for however much time it takes for it to give up the semaphore. As soon as it gives up the semaphore by doing a V, that moves the ownership of the semaphore to A, and then A gets put back on the ready queue. We invoke the scheduler. The scheduler says, A's back again, and A gets highest priority, so A gets to run. So now A runs, it finishes its critical section, and then continues processing until it's finished with its compute time, and then it goes to sleep, and then B is allowed to exit. Okay, this is an example right here of where we have a process A that is the highest priority process that wants the CPU, and it isn't asleep. It's not like it's dead time between when it's finished its compute time and when it hasn't been reinvoked again. Well, we've got a situation right here where the highest priority process is not allowed to run because the lower priority process owns the semaphore that protects the critical region. This is what you call a priority inversion. Effectively, B is running as if it were the higher priority process by virtue of the fact that it owns a semaphore that the higher priority process wants. So is this a bad thing? No, it's not a bad thing, because the reason why we have this situation right here is to protect the critical region. We have to give priority, in some sense, to the idea that the critical region has to be preserved. If we don't preserve the critical region, and the fact that a critical region must be accessed atomically, if we don't preserve that fact, your bus is going to crash. Your missile is going to slam into the bus that just crashed. Bad things will happen. Your program will not work correctly. We've already seen that. It will produce incorrect results. So your embedded system will fail. Okay, so we have to protect the critical regions, even in the presence of the idea of priority. So it's more important to preserve the atomicity of a critical section than it is to make sure that the highest priority process is the one that's running. So we make sure that we preserve the critical section, even at the expense of having a priority inversion. The problem that we need to address is the fact that this priority inversion can cascade beyond just these two processes. So if you note, all that process A has to wait is for when process B does its critical section. As soon as it's done with its critical section, A gets to run. It would be bad if A had to wait for not only process B to finish its critical section, but also for it to finish all of the rest of its compute time. That would be inappropriate, because what we would have is a situation to where a lower priority process gets to run when the higher priority process wants to run, and there's no reason why the lower priority process should be running instead of the higher priority process. So that's a situation that we want to avoid. Okay? So, priority inversion is not in and of itself a bad thing unless it leads to worse things. What are the worst things? The worst things are what I'm going to show you in PowerPoint right here. Okay, so we've got, now I realize usually when you put PowerPoint in front of a class, that is permission to close the eyes, go to sleep. There's only like 3 or 4 slides, so bear with me. I don't know why, but people don't sleep through when I've got my notes up here in electronic format and I point at my notes as opposed to pointing at a PowerPoint slide. I don't see much of a difference, but nevertheless, y'all sleep less when it's notes instead of PowerPoint. If you can figure it out, let me know why, and I'll invoke that, or I'll implement that in my teaching style. Anyway, so what we're going to do is show an extreme example of priority inversion. Okay, we've got 4 processes, A, B, C, and D. Okay, each of them have a priority. We have this execution sequence and a release time. The release time corresponds to when is this process released so that it wants the CPU. The execution sequence, we have E, Q, V. So each letter represents a tick of time. How much tick? Well, it could be a millisecond, a microsecond, however much corresponds to your interrupt, your timer interrupt period. So E just means I'm executing, not owning any semaphore, just executing, just doing compute time. Q means I'm executing, but I'm executing while I am in a critical section that's protected by semaphore Q. Okay? So, in other words, process A wants to execute not owning any semaphores, then wants to execute for 4 ticks owning semaphore Q, and then just execute, then release semaphore Q, then just execute for a regular old cycle after that. Process B just wants to execute for 2 ticks. Process C wants to execute for a tick, and then execute with semaphore V for 2 ticks, followed by just executing for 1 tick. Then process D wants to execute, and then execute 1 tick with Q, release Q, execute 1 tick with V, release V, then execute for 1 more tick. Okay. So here is the fun little scenario. So just let me, since this all doesn't fit on the slide, let me show you the key here. We've got different colors of boxes corresponding to different ticks of time. Okay, so if the box is colored blue, that means you've got a process that's just executing. If the box is colored yellow, that means you're executing and you own Q. If it's green, you're executing and you own V. If it's white, that means you're not executing because somebody else is executing. You're preempted. If it's red, that means you're blocked. That means you're waiting for a semaphore to become available. You can't run. So white is when you're on the ready queue. Red is when you're on the blocked queue. And one of those 3 is when you're running. Okay? So what we have over here, we start by releasing process A. Process A is the lowest priority process. Sorry, process A is process A is the lowest priority process. Process A gets released, and it executes for 1 tick, then it runs owning Q for 1 tick, and then process B and process C get released. These 2 guys are higher priority than A. Okay, so B gets through, so C is higher priority than B. B doesn't get to run because C's higher priority, so B starts off being preempted and has to wait for somebody else. So C gets to run because C is the highest priority ready process. So C runs, just executes for a tick, and because, like we showed on the previous page, it wants to run, just execute for a tick, then own V, execute for a tick. This is what it tries to do. So it executes for a tick, it grabs semaphore V and executes for a tick, and at this time, it would ordinarily try to execute for another tick owning V, but at that point, the highest priority process, process D, gets released, and because D is highest priority, it gets to run. So D executes for a tick, then executes for another tick. During that time, everybody else is preempted, and at that point, process D attempts to grab a semaphore. Which semaphore does it attempt to grab? Attempts to grab Q. Okay? So it wants yellow, and it can't have yellow. Who owns yellow? A currently owns yellow. So process D gets blocked. So he gets blocked on process Q's, or semaphore Q's, block Q. And so we just pick the next highest priority process that's ready, which is C. So C executes with V for a tick, releases V, executes for 1 more tick without owning any resource, and then it goes to sleep. Okay? So then the scheduler goes through and says, well, okay, I'm going to pick the next highest priority process to run. That's process B. So process B has been waiting this whole time and now gets to execute just for 2 ticks. Process B doesn't even want any semaphores. It just wants to run. And because he's the next highest priority process, he gets to run. Execute, execute. Great. Now process A finally gets slots back in. And note, this whole time, the highest priority process is waiting patiently for its resource. So process A gets slots back in, and process A gets to finish its other 3 ticks executing with Q, and finally releases the semaphore. And now process D up here gets to execute 1 tick with Q, and then 1 tick with V, and then gets to execute for 1 tick without owning anything, and then it suspends, and finally we get to finish A. Okay, the problem with this is that you have process D, the highest priority process, has to wait not only for the process that owns the resource it wants, but it has to wait for guys in the middle that have nothing to do with this. Okay? So effectively, if you look at, we have C gets to run and B gets to run, and effectively A gets to run almost to completion before D gets to run. We have a priority inversion, not just between the process that wants the resource and the process that owns the resource, but we have an inversion of all the processes. So everybody else gets to run instead of the highest priority process. This is where priority inversion gets you into trouble, okay? Because everybody gets to get in line ahead of the highest priority process. So, how do we say this? That's bad. We don't like this. This is bad. Okay. Back to notes. Now you can wake up. Must be a sedative built into PowerPoint somehow. Microsoft's probably done some research into that one. How to put people asleep. You show PowerPoint. Boom. Okay. So, the problem is not that a lower priority process forces a higher priority process to wait while the lower priority process completes the critical section. The problem is that everybody else in between gets to run. Okay? So when all the processes run before the highest priority process, even though they don't share a critical section with the highest priority process, that is priority inversion. So now that we know what the problem is, that you have everybody gets to get in line before the highest priority process, how do we prevent that from happening? Reassign priorities. So we have a fixed priority assignment that won't be fixed anymore. So these are basically the ideas. Yeah. So what we're going to do is we're going to change the process's priority. Okay. So and what that'll do. So basically, both Mitch and Derek are right. So we're going to change the process's priority, and we're going to allow the process that owns the resource to execute with priority over the processes that have nothing to do with the shared critical section. Okay, so this concept is called priority inheritance. Okay, so when a process owns a semaphore that a higher priority process wants, the problem arises when that lower priority process gets preempted. So what we want to do is only allow the higher priority process to be blocked at most one time. So, or by at most one process. So we want to make sure that if a lower priority process grabs a semaphore that a higher priority process wants, we have to make sure that that higher priority process will only get blocked because that lower priority process owns the semaphore, not also due to the fact that every process in between also has higher priority than the low priority process that owns the semaphore. We have two approaches that have been asserted for this. One's called the original priority ceiling protocol, and the other is called the immediate priority ceiling protocol. So we'll first talk a little bit about the original priority ceiling protocol, then we'll talk about the immediate. Okay? So the original priority ceiling protocol goes as follows. All processes are assigned a static priority. This is what we've been doing already. So every process has a priority. All the priorities are different. Okay? Point two, all shared resources is assigned. Okay, so this all. Yeah. Every shared resource is protected by a semaphore. Every shared resource is assigned a static ceiling priority. And we calculate what the ceiling priority of a resource is by virtue of we tally up who is going to share this resource, which processes are going to share a resource. The static ceiling priority of a resource is the maximum priority of any process which shares the resource. So if I've got 10 processes, 3 of them share a particular resource, I figure out what's the highest priority, the highest static priority of these 3 processes that share this resource. The maximum priority of those 3 processes that share the resource will end up being the ceiling priority of that resource. Okay? So, once we establish, and what this implies is that we have to know at design time what are the processes that share which resources. Which resources are? We have to know what are the processes. We have to know what are the resources, and which processes share what resource. Okay. Point number 3. Each process has a dynamic priority. Okay. What is the dynamic priority of the process? The dynamic priority of the process is the priority that the scheduler uses when it makes decisions about who to schedule. The dynamic priority of the process is assigned as follows. It's usually equal to the static priority of the process, unless the process owns a resource. Okay, so the dynamic priority is the maximum of the static priority and its inherited priority. How do we inherit priority? We inherit priority, yeah, got him. No audio again? Hello? Oh, okay. Thanks, Gautam. Okay, so never mind about no audio. All right. Each process has a static priority. All the resources have a ceiling priority, and the process has a dynamic priority that's the maximum of its static priority and its inherited priority. Where does its inherited priority come from? So that comes from this dealing with how do we, when we grab a resource, something has to happen. So we raise a task's priority when a competitor attempts to lock a resource. So let's suppose that a process is running along and it grabs a semaphore. Well, it grabs the semaphore and it attempts to execute the critical section. If we go on and later on that process gets preempted, we let it get preempted. And then another process will go on and run. As soon as some other process with higher priority than the owning process attempts to grab that same resource, we tell that process, okay, well, you can attempt to grab it, but you're going to have to wait because the owning process owns the semaphore. Ordinarily, that would cause the second competing process to get put on the block queue. But because of the fact we're doing this dynamic priority, we not only put the competing process on the block queue, but we also elevate the priority of the owning process to the ceiling priority of the resource. Okay? So this is the second step that we do because we've got some other process that wants this resource. Not only do we block that second process, but we elevate the priority of the process that owns the resource. And that gets elevated to the ceiling priority of the resource. Okay? And then what that allows us to do is it allows the owning process to now execute at a higher priority. So it gets priority over everybody that's between what its static priority was and what the ceiling priority of the resource is. And it allows it to complete the access to the critical region sooner. That doesn't mean that it now can't get preempted. An even higher priority process may become ready, and it can still preempt and cause the owning process to go and do other things, or to get put on the ready queue, so the higher priority process can still run. But if that higher priority process attempts to lock the resource, then we'll elevate the owning process again until it completes its critical region. Okay. So this whole notion of you elevate the priority of the process as a competitor grabs the resource, what that does is it allows that lower priority process to execute with higher priority as it's in the critical region. Its priority, its dynamic priority, goes down as soon as it gives up the resource. What that means is that the process that's competing for the resource only gets blocked once. Because what that implies is if this competing process comes in and attempts to lock the resource that's already owned, he gets blocked once. We elevate the priority of the owning process to that level of priority, and then he gets to run to completion, and then he will go back down to a static priority, will grant ownership to the competing process, and the competing process will now be able to enter its critical region. There is no chance for everybody that has priority between the competing process and the low priority process to win. So we don't get this whole priority inversion with processes that have nothing to do with this critical section. Okay. How many of y'all are confused? That's the problem with the original priority ceiling protocols. It's confusing. Okay? So what they did is they changed the protocol and they implemented what we're going to be implementing, and that's the immediate priority ceiling protocol, the IPCP. And we call this PCP, or priority ceiling protocol. Okay? What we're going to do with the immediate priority ceiling protocol is instead of a process that grabs a semaphore and executes, its dynamic priority with the original priority ceiling protocol its dynamic priority doesn't change until somebody else also wants the resource that it owns. With the immediate priority ceiling protocol, what happens is we predetermine what the ceiling priority of the resource is, and as soon as the low priority process grabs the semaphore, its dynamic priority elevates to the ceiling priority of the resource. Okay? So it doesn't matter if there isn't another process that has to attempt to grab the resource. It's just you attempt to grab a shared resource. If you own it, if you succeed at grabbing it and you don't get blocked, then your priority gets elevated. So what does it get elevated to? It gets elevated to the maximum priority of any process that wants that resource. So what that implies is that no other process will have high enough priority to get a chance to ask for the resource, because of the fact that your ceiling priority, your owning process will execute at the ceiling priority of the resource. Okay? So any process that attempts to grab a shared resource according to the priority ceiling protocol, if it has a high enough priority to grab a resource, it will win. It will get the priority. With priority ceiling protocol, there is now no longer any such thing as blocking. Why would there be no such thing as blocking? The time where you block a resource, or you block a process, is when you have one process that owns a resource and another process that attempts to grab it. We're going to prevent the ability to grab it. How do we prevent the ability of another process to grab it? Well, we don't let any other process attempt to grab anything, because we raise the owning process's priority to a level that's equal to or higher than anybody else's priority who wants to grab it. So once my priority is raised, they can't run. They get to sit on the ready queue. Even if they're made available to run, my priority is higher than them, so they can't run. They get to sit and wait. They're preempted. They're effectively blocked, but they get to sit on the ready queue as opposed to a blocked queue. They don't have high enough priority to attempt to grab a resource that's already owned. So we now no longer have blocking with a priority ceiling protocol because of the fact that you can't get a chance to do a P on a semaphore that isn't available. You don't have enough priority to get swapped in to attempt to do the P. So because you can't attempt to do a P on a blocked resource, you can't ever get blocked. You just stay preempted until the process that owns the semaphore relinquishes it, and its dynamic priority goes back down. It's much clearer, huh? Derek agrees. Yeah, much clearer. Mitch.
We don't care about the fact that now every time we enter a critical section, we might be elevating our priorities until we don't need to.
Okay, so the question is, do we care about the fact that every time we enter a critical section, we're elevating our priority even though we may not need to? That's the disadvantage of the immediate priority ceiling protocol, is that you will elevate your priority no matter what, even if you don't need to. So we acknowledge that, and yes, we don't care about it. But what it does do is it preserves the schedulability analysis, and we'll do response time analysis for the priority ceiling protocol towards the end of these set of slides, and I'll these set of notes. They're not slides. Y'all are awake. That's why the benefit that it provides us with schedulability, being able to do the analysis on the schedulability, outweighs the fact that we have to elevate the priority all the time. So, with the priority ceiling protocol, how we're going to implement the priority ceiling protocol is by use of semaphores. Okay? The whole priority ceiling protocol is centered around the fact that if you attempt to grab a resource that's already owned, well, how do you grab a resource? Well, you call P. So you grab the semaphore that protects the resource. So we're going to implement a new version of semaphores called PCP semaphores, priority ceiling protocol semaphores. So we'll have a new type of semaphore called PCP sema, and we'll have a PCP-P and a PCP-V. Okay, so here's an initial version of the priority ceiling protocol implementation. Okay, and again, this is the immediate priority ceiling protocol. So we first disable the interrupt, and then we query the count on that semaphore, and we say if the count is greater than 0, decrement the count. That means the semaphore is now available. Decrementing the count means that the one slot that it had is now no longer available. Now what we need to do is move the running process to the ceiling priority. So again, as soon as somebody grabs the semaphore, we're going to immediately elevate its dynamic priority to be the ceiling priority of the semaphore. If you see right here, we've got an all processes array and a hold processes array. The all processes array is an array of process pointers that's indexed by your scheduling table. So if you remember, your priority queue is now that table, and that table, all that it does is it tells you what's the highest priority ready, what is the highest ready priority. It doesn't tell you a pointer. You use that priority then as an index into an array. Okay, this is that array, the all processes array. It contains pointers to all the processes indexed by priority. S arrow ceiling, that's a field inside the semaphore structure that tells you what is the ceiling priority of the semaphore. How do we determine the ceiling priority of the semaphore? Again, we have to know beforehand what are all the processes that share this semaphore. What are all the processes that are going to attempt to grab this semaphore? We take the maximum static priority of any one of those processes, and that is of all of those processes, and that ends up being the ceiling priority of the semaphore. Okay, so this we do at design time before you release all your processes to run. Okay, so we set all processes bracket S arrow ceiling bracket. So what we're going to do is we're going to replace in the all processes array the pointer to a process that has the ceiling priority. We're going to replace it with an entry in the hold processes array that's indexed by the priority of the running process. Okay? So move running process to ceiling priority. What this does is it says process running arrow priority equals S arrow ceiling. And then we say all processes S arrow ceiling equals hold processes proc running arrow priority. So what this is doing is it's saying, this is a bug. Anyway, I'm going to give you another version of this. This is not the thing you're going to implement. This has got a bug or two in it, and more than just this. But anyway, this hold processes array has all of the processes indexed by their static priority. The all processes array has all the processes indexed by dynamic priority. And the all processes array, we juggle around which entries in that array correspond to which slots of priority as we change the entry, as we change a process's dynamic priority. The entry of the hold processes array never changes. So this is how we remember which process actually has what static priority. So as we go through this hold processes array, all that we do here is we just grab an entry in the hold processes array and we copy it over to the all processes array. Okay? We never write to this one except for when we create a process. Okay? So we copy over to the all processes array at the slot in the ceiling, at the ceiling priority slot, the pointer to the process. Effectively, we could just comment out this hold processes business and just put process running right there. All that we're doing is we're putting ourselves in the all processes array at the slot indicated by the ceiling priority of the semaphore. Then what we do is we do this queue insert into the ready queue address of all processes S arrow ceiling. What this is doing is it's going to say, okay, I'm going to insert the running process into the ready queue. Why do I need to insert the running process into the ready queue? Well, if you've just changed the priority of the running process, you want to make sure that your tables get updated with the right priority. So we want to mark the ceiling priority of the semaphore as being ready. So that way if the scheduler ever runs, while this process that owns the PCP semaphore is in the critical section, the scheduler still has to decide that this process that's currently running is ready. Otherwise, your scheduler will swap it back out because it'll think that the static priority is not the same as its dynamic priority. So you have to make sure to mark the ceiling priority in the tables. Okay, PCPV. How do I give back a PCP semaphore? Disable, increment the count, set the all processes arrays slot at the ceiling priority of the semaphore equal to whatever it was before. So what we're going to do is we're going to copy into that slot hold processes sub S ceiling. So before we replaced the ceiling priority slot in the all processes array with a running process. Now we're going to replace it with whatever process has static priority equal to the ceiling priority of the semaphore. Then what we do is we say that the process running priority is equal to the process running static priority. This unelevates the running process. And then what I say is if the process that has the original process whose static priority is equal to the ceiling priority of the semaphore, if its state is blocked, then I mark that process as not being ready. So just like before, when I elevate a process, I have to mark the corresponding entry in my ready queue table as ready for the ceiling priority so I don't get swapped out inadvertently. And here, I've got to mark it as not ready anymore because I'm reducing the priority of the running process. There is a chance that, and this is encountered quite frequently, that when the process that owns the PCP semaphore is running while it owns the PCP semaphore, that the process whose static priority that's equal to the ceiling priority of the resource that we're accessing. So all processes, so this process that has the ceiling priority as its static priority, that process could have been made ready. We only clear the entry in the ready queue corresponding to the ceiling priority when that ceiling process is still blocked. It's possible that it's not blocked anymore. If it's been released, we want to make sure that that entry is still asserted in the priority queue. Otherwise, you have a ready process that isn't ready. Okay. PCP semaphores guarantee mutual exclusion by forcing the owning process to preempt all the other processes that share the semaphore. So no other process is allowed to have sufficiently high priority to ask for the semaphore. So they never get blocked, they just never run in order to compete. They don't get to compete. Okay. So the whole two questions need to be addressed. Do we really need a count? Why do we need to keep track of whether or not the count on the semaphore is 0 or not? If a invoking process attempts to grab a PCP semaphore and they get past the disable, they will get the PCP semaphore. And they will preempt everybody else that could attempt to grab the PCP semaphore. So we don't need a count. We don't need to keep track of the count because if you ask for a PCP semaphore, you're going to get it. You can't not get a PCP semaphore. Okay? So what this means is when you do a PCP-P, there's no else. So right here, we don't really need a count. You should just say, give the calling process the PCP semaphore. There should never be an else. If the PCP semaphore is unavailable and you've attempted to ask for it, then your implementation's messed up. So you should never get into a situation to where you've attempted to grab a PCP semaphore and that PCP semaphore is not available. Okay? So that's why you have in this else clause a print saying error. We should never block on a PCP semaphore and you exit. It's kind of weird because if you ask for a PCP semaphore, that means your priority is high enough to be able to ask for the PCP semaphore. That means no other process that has higher priority than you currently wants the CPU. So if your priority is high enough to ask for a PCP semaphore and you get past that disable inside PCP-P, you will get the PCP semaphore and you will prevent anybody else from having high enough priority to be able to call PCP-P. So you will run because your priority immediately gets elevated and nobody else who wants that PCP semaphore will even be able to allow to ask for the PCP semaphore. Yes, I know, it's weird, it's odd, it's confusing, and I'm going to lecture about it next time too. So I'll try to clarify things. First, what we're going to go through is response time analysis. So if you remember the response time analysis, the whole point about PCP semaphores is to keep us from infinitely blocking or having this priority inversion. How does the use of PCP semaphores impact the response time of a task? So if you remember, we've gone through this math before where the response time of a task is the worst case time in which it takes for a task to finish its compute time. And we have to prove that the response time is less than its period. So what we're going to do is we're going to introduce a new term to our response time equation where the response time for task I is equal to the sum of its compute time plus its interference time and its blocking time. Okay? Interference time, again, if you remember, is the time that a higher priority process runs in favor of a lower priority process because it's higher priority, because it is higher priority. So interference time corresponds to when am I preempted. Okay? The blocking time is when is a lower priority process executing that owns a resource that I want. Okay? So this is the time that we're blocked due to somebody else owning a resource that I want. Interference time is when is there just a higher priority process that gets to have the CPU by virtue of the fact that they are higher. So interference time comes from processes that have higher priority than you. Blocking time comes from processes that have lower priority than you. Okay. By virtue of the priority ceiling protocol, you can only get blocked once. And that's because when a lower priority process attempts to grab a resource using the priority ceiling protocol, their dynamic priority will get elevated to the point to where they finish their execution run for that resource, and then their dynamic priority will get reduced back down to a lower level. If you don't become ready during that time where that lower priority process is running, then nobody cares. This doesn't matter. You're not going to get blocked anyway. Okay? The time where this is relevant is if the lower priority process, if it is able to grab a semaphore, then what that means is the time at which they grabbed the semaphore, the higher priority process was not ready. If the higher priority process were ready, the lower priority process wouldn't have had high enough priority to be able to ask. It would have been preempted. Okay? So the lower priority process is the only one that's trying to run for a little bit of time, or it's the highest priority process that wants the CPU, and it grabs the semaphore. At that point in time, it gets the semaphore and it starts executing the critical region. If, while it's executing the critical region, I become ready and I'm higher priority than him, I'm officially blocked because he owns a semaphore that I want. Okay? During this period of time, I am blocked. How long will I be blocked for? Well, for as long as it takes the lower priority process to operate the critical section. Okay? So, and then I'm guaranteed to be able to allow access to the critical region as soon as he gets rid of the semaphore. So I can only be blocked at most for the biggest time that I can be blocked for is the amount of time that a process owns the shared critical section. Okay, so we have this equation right here. You can only get blocked once. So B sub I is calculated as the max over the product of this term usage Ki times C sub K. C sub K is the amount of time that I spend in the critical region. Okay? K is the resource number. Okay, so max K equals 1 to cap K, usage K sub I. Usage K sub I, this says, this evaluates to a 1 or a 0. And again, this is another one that's going to break your head. Okay? Can process I be blocked by someone owning resource K? If so, this evaluates to a 1. Okay? So how can process I be blocked by somebody owning resource K? So the somebody who owns resource K has to be of lower priority than process I, and resource K has to be wanted by somebody with equal priority or higher priority than process I. Okay? So what this means is that, again, because when a lower priority process grabs a semaphore, its priority gets elevated to the ceiling priority of the resource. Okay? If that ceiling priority is higher than my priority, my static priority, I get blocked. Okay? So what this is just saying is if some process grabs a resource, and if that could potentially result in process I getting blocked, this term evaluates to true, to 1. So what I'm going to do is I'm going to calculate in the worst case for all those resources that can be grabbed by a lower priority process than me that I can end up getting blocked by. I'm going to figure out what's the biggest compute time that any one of those resource grabbings will result in. So the length of time that I can be blocked by is when that process grabs that critical section, how long are they in the critical section for? So I just figure out what's the longest critical section time by some lower priority process that can end up blocking me. And that tells me what the blocking time is. I only have to find the one biggest time because I can only be blocked once. Okay, so the equation for the response time analysis ends up being this, where your response time is the sum of the compute time. This is just the expansion of the interference time, and this is the expansion of the block time. So anyway, we can now do math to prove whether or not our processes are schedulable. I'll go over some more of this next time, along with the real implementation of the priority ceiling protocol semaphores.
Just because we can analyze this one.
Did you just call me Dr. Moon?
I called you Dr. Brown.
Oh, okay. I've been called worse.
It's a massive garbage up here.
Especially after my lecture.
Wouldn't the other one, the first one, be better?
The original?
Even though we can't analyze it?
No, you can analyze it, and it does the same thing. The blocking term is exactly the same, because you can still only be blocked once. What you got to think about it is the time at which the total time that the CPU takes is the same. It's just you're rearranging when on the timeline does the process that owns the resource get to execute. So what you're just doing is you're shifting the time where it owns the resource earlier in the timeline. So whereas before you can allow a higher priority process to run so long as it doesn't want a resource. Okay? And as soon as it wants a resource, then the owning process's priority gets elevated and it gets to run, and this guy gets blocked, and it'll run for a little while. With the immediate priority ceiling protocol, what you're doing is you're just rearranging these two processes' timelines. So you're letting the slots that the process that owns the semaphore just shift earlier, and these guys just shift a little bit later. But the sum of the two end times remains the same.
So wouldn't that be not? Wouldn't we prefer the first case over the second one?
In some sense, it makes more theoretical sense to do the first one. Yeah, it's more preferred because you are having less priority inversion, but the end result of both of them is the same with respect to response time. So theoretically, if the response time is the proof, both end up being the same proof regardless of which algorithm you're using, and it's much less touchy to implement the immediate priority ceiling protocol.
But in real life, they
use the immediate because they
decide the first one's better.
No, theoretically the first one's better. Implementation-wise, real life, the second one's better because of the fact that you're not going to have so many bugs that are going to cause things to crash.
So a process can still get interrupted though by another process that doesn't want.
Yeah, an even higher priority process that has nothing to do with any of these resources. Yeah, the whole point is that any higher priority process that is higher than the ceiling priority of the semaphore, it can still run.
But when we bump it up, that's only higher for the static one.
We bump it up to the ceiling priority of the semaphore. There may be processes that have even higher priority than that. I'm going to give you some math problems to do for this, so it will hopefully make a little bit more sense.
Oh, yeah. Math always makes more sense.
Yeah, math helps.